Okay, so now for our last talk, we'll have Marc and Farhad talking about type-directed API search for mainstream languages.
Great. Thank you. Hello, everyone. I'm Farhad Mehta, and this is Marc Etter. Marc is a master's student. He just finished his master's, and this was his project. Both of us work at the OST. The OST is a university in Eastern Switzerland, not very far from here. Maybe some of you already know it from Zurich. Who's been to Zurich? Okay, very few. So for those of you who haven't, feel free to come by. It's in June. I guess you'll have fun there. Good. Second question. How many of you have used Hoogle? Oh, wow. Basically, almost everyone. Okay, good. That's good. I don't have to do a demo for Hoogle, at least. Great. So I'd like to tell you a little bit about how this project got started. Yeah. So Marc was actually doing his master's thesis with me on something totally different. It was correctness of Java programs, and I mean, this is now 2024. Who cares about correctness of Java? We have other problems. But anyway, we were working on something, and we were looking at some code, and Marc told me that, hey, we have to search for a function like this, and then he told me, yeah, it would have been nice if we had something like Hoogle, but for Java. And I said, well, we're not in functional land right now. Java people don't get nice things. There is no Hoogle for Java. And he said, okay. And then I said that, yeah, but this is not unfortunate. This is unfortunate that you didn't think about this earlier, because this could have been your master's thesis project. And he said, okay. And then I said, but we have a solution. I can fail you for this, and you have one more try. And then you can try this for your master's project. And Marc didn't think this was a joke, and he said, yeah, let's go with this. And I was like, okay, good. Then we did that, and now we're at ICFP. Good. So this is how this happened. Anyway, so now we're here. So a typical scenario for a developer is that he or she wants to search for some function in some huge library, right? The standard libraries are huge. Stream language. So what people normally do is they bring out their web search, yeah? Type the function they want. Yeah? I want a function in Java for blah, blah, blah. And then Google gives them the search engine gives them some answers, yeah? And then they click on that, and then they see some Stack Overflow posts and all that stuff. Okay, but this is all text-based, right? But what we actually want is that we want something that's specification-based. And specification, the only thing that we have currently as a formal specification for most languages is the type system. Yeah? So types are a form of specification, or maybe the most formal specification that many languages have today. Yeah? And so the idea would be very close, that we would need something like a type-based API search. Yeah? And this idea is not new, as all of you know, right? There are many people already use this for Haskell, right? And some other languages. But this idea is only possible for very few. So Haskell is one of them. There are some more. And we had a paper in Splash 2016 where we tried to do this with Scala, but this was with a standard web search technology. And the work that Marc will present now will be basically something like Hoogle, but for a general mainstream programming language. Yeah? So what makes this approach appealing, yeah, compared to the other approaches that we've seen till now? So this is targeted at mainstream, that means typed OO languages. Yeah? So we have subtyping, not just polymorphism, ad hoc and parametric, but also subtyping. Yeah? And its inspiration is the Curry-Howard correspondence. So we try to make it not ad hoc per language, right? But we try to distill out the common features of most mainstream languages, and we try to use this idea of proofs as programs to sort of get out these terms that we want to search for. Yeah? And when we do this, yeah, type search becomes proof search, with all the nice techniques that we know with proof search. And one of the surprising things that we found out was that it was even possible to synthesize code from these searches. So in Hoogle, right, when you give it something to search for, it'll give you the functions. But with this approach, what we could also do is we would combine these functions to give out a term which would match this particular type. Yeah? So this is something unexpected that came out later. Yeah? So this idea of using type systems to have a problem, to generalize a problem to such an extent that the solutions that we get are not only general for the language that we use, but also for the solution space. And so we were quite surprised when we saw that. In any case, now Marc would like to tell you some things about the actual technique that we use.
Okay, so I'm gonna present the prototype implementation of this concept. So at first we start with an API source. So this is just any library, it can be the standard library, it can be a third-party library. We need to scan this library, parse it, and we call this source extraction. We collect all of the type information out of these libraries, store them in some convenient database. We have our internal model for this that I'll go into later. And this is the basis of our search that we then search through. All of this can be done as pre-processing so that we don't have to do all of that when we actually execute our queries. So then when the user starts using this tool, they start by running a query. We then run our proof search on that query, which combines the query input together with what we have stored in our index database. We build proof trees. There can be multiple proof trees because there can be multiple ways to arrive at a solution. We rank those trees amongst each other so that we can have the most relevant search results at the top. And then we display those search results in a web UI. Now, the interesting part, especially regarding towards mainstream languages, not only for Java, is that only the first two steps are language-specific in this implementation. So, of course, the source code of the libraries is language-specific, then the extraction is language-specific, but after that, all of the internal model and all of the search implementation only works on this internal model. So once you have translated any library code into this internal representation, you can search for it with the same query syntax. Of course, the display of the search result is then nicely pretty printed in the language that you actually requested again. So how does the source extraction look like? So for a Java function to string of a class integer, we transform it to a syntax that's very reminiscent of Haskell type signatures. So we get something like that. We also label the function so that we know where it came from, because in the end, the search result, we need to know what's the function that the user should then use. So here we get a function integer arrow string. If we have a static function on the class string that takes an integer, returns a string, it's kind of slightly different, but in the end, it kind of does the same thing. And in the internal representation, we can see that the signature is indeed the same, even though in Java it's kind of different, has a different label because it comes from a different place. And then a bit more interesting example here, we have a type, this interface list has a type parameter e, and if we transform this into the internal representation, we get this for all e. That is very normal for Haskell syntax. So we have a set of proof rules that we then use to build our proofs. I'm not going to go into the proof rules in detail, but just here as a quick overview, we have 6 proof rules, and these are all the proof rules that we need to perform all of these proofs, including parametric polymorphism and subtyping. And on the right side, you can see an example of a proof that we build with these proof rules, but I'm going to build one now step by step so that we can see how this works. So the very first thing that happens, well, apart from all of the source extraction that I just showed some examples of, is that the user inputs a query into the web UI. This query syntax is defined in a way that it's a bit convenient for someone that's more used to OO languages, so it's not an entirely functional structure, as you can see with the comma there denoting the parameters. And when we parse this into our proof syntax, we parse this into the goal of the proof, so the right-hand side. This is ultimately what we want to find a proof for. We give it a label G for goal, and the various types, you can see they are transformed quite straightforward. We collect any type parameters in the query into these parameters. So now that we have this goal, the first couple steps are to normalize the goal. We do this, the first thing that we want to normalize, we want to get rid of these for all clauses. And we can do this by instantiating this A with a fresh type f that we just invent. And by applying this, and we basically just replace every occurrence of A with f. So now we don't have any like free variables anymore that we can assign. So next step is to get rid of all the arrows in the goal. And we do this by kind of introducing terms on the left-hand side with these types. We call them G1, G2, etc. So now we end up with a term on the right-hand side that only has the type streamf. And since it now is just a single type, yes, it's a constructed type, but it's still just a single type, no functions, no type parameters going on. We call this a normalized goal, and now we can start searching proofs for this kind of type. So for the moment, let's ignore the right-hand side. Now we're working on the left-hand side, because we need to construct terms and combine terms. Here we have one function. You can imagine there would be tons of functions in our proof context. Each function here, or each term, represents one of the functions that we previously extracted out of the API source. And here is just this filter function, which is the function that we conveniently will end up finding. But this again is a polymorphic type or polymorphic function with this t. And again, similar to the goal normalization here, we will instantiate this t as the first step. And we choose to instantiate this t with f. There are various heuristics and ideas how to choose which type we want to instantiate this t with. I'm not going to go into them in detail right now, but here we just choose f. Then the next step, we can resolve this term by applying other terms to get rid of the arguments that this filter requires. And here we can pass G1 and G2, because G1 has this type streamf. Now, if you've been paying attention, you might notice, hold on a second, G2 doesn't actually have this type predicate f, it has type f arrow boolean. So why are we allowed to apply G2 here? Well, the reason is that during source extraction, this is something that is a little bit specific to Java, is that Java has these so-called functional interfaces, and we represent this with type mappings. So we have different types that aren't strictly equivalent, but due to particularities of the language, they can be viewed as equivalent. So this could be like implicit type conversions and stuff like that. And in this case, we learned from the Java language specification that this type for all t predicate t is equivalent to t arrow boolean. And with this knowledge, we're allowed to use G2 in this place where predicate f would be expected. So now after we've applied these resolution steps, we've ended up with a term on the left-hand side that has the exact same type as our original goal, or as our normalized goal, I should say, on the right-hand side. So now we can apply unification, and we get the result that filter successfully unifies, and so we can include filter as one of our search results. And of course, this would be then repeated for any other term that would also successfully get such a proof, and then we could get multiple search results, rank them, etc. So this is a screenshot of the web UI, and in this screenshot you can see is the exact query that we just showed, that we went through in this example, and we can see filter is listed as the second search result. The only better search result here is drop while. It has the exact same type signature, so it's equally good match, and it's just first because it's come first alphabetically.
Yeah, cool. Thanks, Marc. Of course, no demo is complete without a live demo. I forgot about doing that later, so some chance of failure. Let's take a look. See that it really works. wanted to do one about Hoogle as well, but Hoogle, we all know that, so let's try this here. So this is the query that Marc currently just showed you in the proof as well. So if we take a look at this, click it, and you see it currently, in this time that we clicked at it, it showed a number of results, and one among them was the filter that we were searching for. Yeah. So currently, this is for more languages. Currently, we only have one instantiation for Java. Someone expressed interest in doing it for Go, so we're open for anyone else who would like to try something here, right? And yeah, that's the demo. Let's go back to the presentation. Okay, yeah, so what's the further work? What can we do? What wasn't done yet here? So one thing that we could do is to make use of pre-existing search algorithms for proofs. Currently, we have something that's very fine-tuned for just these sorts of searches. But of course, we could use existing algorithms for proof search. That's actually something what one of the reviewers said that, yeah, actually we don't really use the Curry-Howard-Ice correspondence for this because we don't really do any proof search. But actually, there's nothing to stop us from actually using proof search algorithms for this. This is something that we'd like to take a look at. Second thing that we haven't yet done, at least in the prototype that we have, is do actual code synthesis. This is something that's possible, right? And we can get it out, but it's just the search space just explodes. So if we have some better proof techniques, we could maybe even do some code synthesis, which is something that Hoogle, for example, doesn't do right now. Yeah? So you could think of it like this: as you give a search, and they'll say, oh, this function is okay, this function is okay, this function is okay, and this combination of functions is also okay. That would be something really cool, we find. Yeah, and of course, adding support for other languages. Yeah? That would also be something. So any typed language with subtyping and polymorphism would be game for something like this. Good. To conclude, yeah. So what did we find out with this work? So we found out that type-directed API search for mainstream languages is possible, right? And although in the beginning we thought that mixing polymorphism and subtyping would lead to some big problems, we saw that actually didn't, which surprised us because we typically have this idea that subtyping and polymorphism doesn't really go well together. But in this case, they didn't seem to annoy each other too much. Good. And we also found out that all this can be done in a very systematic and language-independent way. So we started with something for Java, right? And we found out that by making things more general, we could support more languages, and it was basically a success story for types. Yeah. And so with that note, I'd like to end this presentation, and we're here for your questions.
Thank you. Questions?
So thanks for the talk. So I think in the early slide, you showed that when the user wants to do the query, so they type some sort of like type signatures. I'm wondering, is this language specific? So for example, if you're using Java, you have a specific syntax designed for Java, and if you're doing some other languages, you have other syntax.
Yeah. So our goal was to make the query not language specific. So we have a language agnostic specification
okay,
for
so
the
query. Query language is?
Yes.
Okay. Yeah, but then a follow-up question is, I mean, when the user types something, for example, if you search in Google, you can make mistakes. For example, you can have some typos, or even, let's say, when you do type search, perhaps sometimes you really don't know, you have no idea what is the correct name of that type. I think this is really common in Java because, you know, they are like very complicated class names, package names, whatever. So like, have you considered like any kind of correction if the user is type something wrong?
Yes. So there are various kinds of errors that a user can make, also just incomplete knowledge about what you're looking for. We've accounted for some of them, not for all of them. So for example, if you omit a type, so you just forget one type in your signature, it will also find that, but just at a lower rank, of course, than those that match exactly. If you misspell a type name, you will get an error message that this type is not known to the backend. And there are some kinds of wildcards that you can use to specify unknown type.
Yeah, some sort of wildcard patterns.
Yes.
Yeah. But how about like if the user does not even know like the correct syntax for the query language, because I think it sounds is intuitive, right? So maybe people will just write it in an intuitive way, or maybe actually this is not accepted by your parser if you have that.
Yeah. So yeah, if the query is like syntactically incorrect, then the query will not be executed. It will not accept it. So this is something we can improve.
I think this
also,
is
the error
something that you
message
could improve.
is not perfect yet if you mistype the query.
Yeah, but anyway, it's a very interesting line of work. Yeah, thanks for your answer.
Okay.
Thank you. What about gradual typing? So see Python. If we are targeting mainstream, then eventually we go, like somebody said, brutal Python.
So I'm not sure I entirely acoustically understood the question.
So is it possible to adopt this system to gradually typed languages like Python? And what, so of course it is possible, but question, do you estimate the performance of it? So will it be helpful, still helpful?
Well, I mean, it's going to be helpful in the degree of how many type annotations are in the source code of the library, because that's all that we currently have as a basis to go on. So if you don't specify any types, then we cannot help you. If you have 90% of your library has types, then it's going to be 90% helpful.
Thank you. And do you plan to develop a systematic way of mapping the language, so make query language more tied to the language, the input language of your serializer? Because you can imagine people who write C++, they would like to query in C++ probably because they know this language.
Yeah, so this is something that we would have to collect user feedback on, what they feel is more useful, whether a single query for whatever language or a language-specific query. We're open for both, depending on what user feedback looks like.
Thank you. And your extractor reads only annotations, right? So essentially, it does not need a full parsing engine. So you can write extractor for C++.
Yes, exactly. We just need the type information and like the name and the source of the function and maybe some documentation that we show alongside, but we don't need the implementation.
Thank you.
Hi, yeah, thank you. I was wondering, maybe I don't understand it completely, but you say this is more sort of language agnostic than, for example, Hoogle, but it seems a bit to me that if you would translate these Java types to your Haskell-like type system, as you say you do, couldn't you just put it in Hoogle? Like, I feel like you can just seed Hoogle with these types and then search for the types that you search for. Is it very different, or am I missing something?
Well, first of all, if we would transform it to Hoogle, then we still couldn't apply the proof search to it, because that is then still very like this proof specific syntax that we use. So it's more this proof-based, lambda calculus-based syntax that we transform it into, where we then apply the proofs to. So Hoogle does not work on that kind of input.
Okay.
Subtyping.
Yeah, and also subtyping is also an issue.
Right. Yeah, that makes sense.
That we had to solve kind of specifically for OO languages.
Yeah, thank you.
Hey, thanks a lot. I think we all agree if we want one tool, it would be something like that in development. So I was actually wondering, how would you, for example, handle if the arguments are swapped in the search, but then I realize, okay, if you compose things, maybe the thing can discover that I can just prepend it with a swap operation, which I think can very systematically cover some of these searches, like instead of hard coding inside Hoogle or something. But my question is actually more about how do you do the search? So you said you conveniently select the filter and you conveniently show the filter because that's the one. But of course, there's way many more functions inside there. So.
Okay, yeah. I can expand on that a bit. So there was a good slide from the previous talk about the forwards or backwards search. So we do backwards search starting from the goal type. And specifically in the example of the filter, we kind of, our first best guess which type to use as instantiation is the type that we used in the goal to instantiate the goal parameter. If that one doesn't work, then we run into a bit of troubles, but that's our first best guess. And that usually is good enough.
Hi, I think this is a super cool tool. Thanks for the talk. I have kind of an elaboration question, because you said that there is a part of this model where you have language-agnostic proof search, and there's a part of this model where you translate things from the language to a search database. But in your example, you showed this predicate T is equivalent to T implies Boolean. So is that something that happens in the, is that somehow encoded in the database? And if yes, I'm wondering how that works.
Yeah, so this information is gathered during the source extraction, so which is language specific, but then it is stored in a language independent representation. This concept of type mapping is not Java specific. We just have, these are all the known type mappings that we could apply during the proof.
Thank you.
Okay, so I actually have a question. So I have some knowledge of type inhabitation, but for the lambda calculus, and actually a method that also use proof trees, although they might be different from your proof trees. So you generate these proof trees, and there was a slide where you said that then you do some indexing, so as to, I don't know, rank them. Can you give some intuition about that? Because I wouldn't
Yes.
know how to rank, for example, in the lambda calculus.
That's a good question, yeah. So we thought about different ideas how to rank them, and the simplest metric that we use is the length of the proof, or of the proof tree, the height of the proof tree. And this is currently the only ranking metric that we use, and it already provides surprisingly good results, because when you have to, the simpler proofs are usually the ones that you look for, because they somehow combine less complicated stuff, and they seem to be more relevant. But of course, ranking is also very subjective. It's not really an objective truth. So we need to iterate on that.
Thank you. Any other questions? Okay, so let's thank our speakers again.